Welcome everyone. Today we'll be interviewing the authors of CryoSift, which is an accessible and automated CNN-driven tool for the cryo-EM 2D class selection. I am John Aguirre from the University of York here in England, and joining me today from Madrid is Mark Van Ray. Hey Mark, how you doing?
Hello, John.
We got Cryst Renato from Sao Paulo in Brazil. How's it going, Christy?
Hi, hello, from the warm Brazil. Happy to be here again.
Great to have you. Today, we're fortunate to have Stephen Muench from the University of Leeds, also in England. Stephen edited the manuscript that we're discussing today. Hey, Stephen, how are you doing?
Not bad. Bit colder than Brazil over in Yorkshire at the moment.
Indeed, I can certify that. Right, so joining us today to discuss the article, Jan, who's the lead author. Hey, Jan, how are you doing?
Good morning. I'm doing pretty well. I'm from the Scripps Research Institute in San Diego.
I just returned from San Diego. I've been at a meeting there, glycobiology. Scott?
Hi, nice meeting you all. I'm joining you from Florida State University in Florida, where it's overcast, but usually sunny.
Wonderful, thank you. And finally, senior author Mike.
Hi, everybody. I'm glad to be here. I'm Mike. I'm at University of Michigan.
Great. So welcome, everybody. And the first question is coming from Stephen.
Okay. So, Mike, for those viewers who are maybe not familiar with cryo-EM, what specific gap in cryo-EM workflows were you looking to address with CryoSift?
Yeah, so thanks. I mean, we're glad to be here to talk about our project. So the CryoSift paper is relating to a bigger project called Magellan. So Scott and I are a part of a bigger project to automate cryo-EM. So cryo-EM takes images of protein samples, RNA samples, and the problem with it is that it's human-driven and has to be visually based. So humans have to make a lot of decisions. And so we're trying to automate cryo-EM at multiple steps. And this paper is trying to automate this selection of what is good data from bad data, because today a human has to be at every step and sort of holding the hand of the algorithm. And so what we were trying to do was trying to sort of distill our expertise in cryo-EM into an AI-based algorithm to help the community and everyone to be more robust and rigorous, but also to automate routines.
Thank you. I have a bit more of a technical question for Jan. So how does CryoSift combine image features with metadata to improve class quality prediction?
Yeah, thanks, Mark. So we were inspired by Relion's implementation, and we take basically the image features that the neural network has derived and combine it with 6 features that are kind of metadata. That includes the class quality, resolution, pixel size, and we use parameters from a median, deviation, and mean of the mass that we've calculated for these projections. And we've seen that the predictive power of the model is much better when we include those metadata parameters. And the idea is that with higher class distribution, higher resolution, and smaller pixel sizes, we can get sharper, higher quality images that the model can learn from. And in particular, the mass estimator gives us an expected mean, median, and mass, and particles with generally larger deviations are expected to have lower class quality. So we can merge all of these informations together, and the prediction of what is a good class is more robust.
Thank you, Jan.
When training the convolutional neural network, what training data were used, and how did you ensure diversity across the samples? Question to Scott.
Yeah, so that's a great question. That is one we really struggled with. So we really relied heavily on this public database Empire. But we hit a problem, which is that with cryo-EM, you take movies and you align these movies to make a single image, but that movie alignment step is a bottleneck. So in order to make it tractable, we had to limit ourselves to data sets where they had uploaded the images, right? So we didn't have to do an enormous amount of processing work. So we found at the time every data set in Empire that had images that were uploaded. And then we supplemented that with data from our own labs, and then Relion had also made their training data accessible. So we combined everything that we could. That said, there are more, we didn't hit every case, and that is why we made this online tool where people can upload their class averages, and we hope that people will do that, and that way, we can make a prediction about the quality of their class averages, but then they can also correct them if there's a bad prediction. So that's our intent with that.
Yeah, and why do you recommend a quality score cutoff of around 3.5, and what trade-offs does it balance?
Well, thanks, Christy. So it's been a bit of a experience, or like an experience-based decision. Usually the automation process necessitates the selection of a cutoff if you want to completely derive this workflow without user intervention. And our rationale behind the selection is to find the sweet spot between optimum of retaining as many particles as possible, remembering the Reslog relation. With more particles, you usually expect an increase in resolution. But setting a too strict cutoff with low abundant views may result in pseudo-anisotropy during the reconstruction. So you can bias it with the most abundant, well or best aligning classes with the best features. And so we needed to find the sweet spot. And for our implementation in cryosparc-tools, we just selected this sweet spot as being 3.5. But as a side note, users have the option to tweak the parameters the way they want. If you have more noisy data or better data for upper ferritin, for example, you have control over these parameters.
Great, thanks.
Thank you. Another question for Mike. So how does CryoSift integrate into existing platforms such as CryoSparc, that was already mentioned, and Relion, which is very widely used in cryo-EM?
Yeah, so that's a good point. So I think in our opinion in cryo-EM software today, a big part of it is helping people use it and making it easy to use. And so there's so many users of so many different backgrounds that if you can make it more point and click or more, pointed at something, people will like it. And so we started with CryoSparc because they recently released this API that you could use that they call CryoSparc-tools, and that this turns out to be very powerful and helpful for us to write scripts outside of CryoSparc that can run these tools. That's what Jan was talking about. And so that exists now, but the problem is that it's not really integrated into the full stack of CryoSparc. And so that's something that we're trying to sort of talk to the developers about. With Relion, we haven't integrated into Relion, but in principle, Relion offers this sort of external software plugins that could also be working for this project, but we haven't pushed as hard as we did with CryoSparc.
I have a question for Scott. Which evaluation metrics did you use to validate CryoSift's impacts on reconstruction quality, and why were these chosen?
Yeah, so great question. So the challenge is there's no ground truth, right? So the best ultimately the best metric for quality is high resolution reconstruction. But then that has its own challenges, because what is the resolution? So we were really aimed at what is the quality of a reconstruction derived from these automatically selected particles, right? So then, since there's no one metric that works, we use three. We use this well-established Q score, right, which evaluates how the quality of a density around an atomic model, right? So that was one metric. Another one was map to model FSC score, right? So that is another match of an atomic model versus EM density. And then we use this Reslog analysis that my lab came up with several years ago. And so, that plots the resolution as a function of number of particles. And so the slope indicates something about the data quality, and the intercept says something about the reconstruction quality. And so it turned out in this case, the slopes for all these different data sets, they varied substantially. And so that was a good one. And altogether, all three of those gave us some confidence in the quality metrics.
Super, thank you.
Thanks. I had a question for Jan. How might CryoSift help reduce subjectivity or variability between different cryo-EM practitioners during 2D class selection?
Oh, thanks. So this is really at the core of what CryoSift can offer. Besides the automation, the selection process is highly subjective and usually based on experience. If you are less experienced and just started off, it's really hard to say what's kind of an average class quality, what features do you expect in these projections, and what CryoSift can basically offer is an expert-trained neural network with universal derived rules of what is a good class compared to all the others, and the training data set basically. So performance differences usually depend on these class qualities, but our neural network can basically help take away this burden and also educate users of what these classes are. We have this website where users can plop in their projections and inspect these labels and can probably learn more about what a good class is, what a worse class is, and all in between.
Okay, next questions is for Mike. Mike, what major limitations or future extensions do they highlight for improving the tool?
So this project, like we've talked about, involved training an AI model for assessing data. And so a limitation is just we are as good as our training data was as far as the diversity of samples. We think it's pretty good. We've tested it, but that can always be the case, especially with all these pre-trained AI models. And so in principle, extending it like we've talked about via projects in our own lab, projects via the website where people can upload would be a nice way to sort of make it more general. And I think as far as extensions go, we think it would be nice to start building workflows around this where you feel confident in the results. So how would you automate if you're, let's say, loading multiple grids into an instrument and you pick particles and get class averages? Could you start making a workflow that's more, over across multiple grids or multiple sample types would be one inspiration. But we're not there yet. But I think that is probably where CryoEM is going, because that's obviously where fields like crystallography have gone, which is automating and taking you above your we're all very focused on one grid at a time. And I think these projects like CryoSift are trying to move us above that to sort of help us automate.
Linked in with that, I had a question for Jan. Given the rapid improvements within cryo-EM and machine learning, how automated do you think the processing pipelines are going to become? And what are the future challenges for cryo-EM data processing workflows in general?
Thanks, Stephen. That's a very exciting question. What Michael and Scott already mentioned is we have Magellan as part of this effort, and also CryoSift as a contribution to automating the entire workflow. There's been a recent preprint from CryoSparc as well that claim we can now use an end-to-end automation for well-resolved and known targets, showcasing it with GPCRs. There's no real manual intervention needed at all, but for novel targets, and we all embrace cryo-EM for its ability to resolve heterogeneous samples, we would need some level of tailored automation processes that only the community can identify as necessary, and we can build these tools specifically probably for dealing with heterogeneity, like automatic selection of similar looking classes, grouping them together as one idea, or how can we resolve helical reconstructions, which we haven't touched too much on. So community-based software development is very much at the core of how we want to build an almost Swiss Army knife of tailored approaches.
Moving a bit away from the technical things, I was a bit curious how the tool and the paper came together. So the acknowledgement section already gives some information on who did what. Could you give some more details?
Yeah, so this project has been going on for 4 years at this point, I think, five perhaps. And so what this involved was my lab at Michigan, Scott's lab at Florida State, and Gabe Lander's lab at Scripps. And so this project evolved. You can see that the initial training of the AI models was done by an undergraduate in Gabe Lander's lab. And then eventually it sort of was championed by Jan to sort of push this through and to show how it actually worked in cryo-EM workflows. But you're right, the acknowledgement section showed that this is a cross institution collaboration. We have weekly Zoom meetings where we're talking all the time, which is how we were able to sort of put together this idea of a website that's going to be for class averages to be uploaded, as well as Jan showing us how it's working inside of CryoSparc and so on. So it's been a true team effort. We had to sort of put people down on an authors list, but it's been all of us talking about this together weekly for a long time, many months to perhaps a year.
Thank you.
Well, speaking about collaboration, my next question is to Scott. Scott, macromolecular crystallography is known for large collaborative software suites like CCP4 and PHENIX. Or will this also be true for electron microscopy? CryoSift seems to be a step in the same direction, right?
Yeah, that's something I think about a lot. So, because I can see both sides. In cryo-EM, we have a lot of people with really creative, fun ideas, and they try it and it works. And it's like, oh, that's great. And then, so that's from a developer end. And then on the user end, it becomes completely intractable to try to download and figure out all the parameters and like how to install these different softwares. And so we're not there yet with like a one big uniform software package, but there's a lot of initiatives in the direction we're not the only ones to have this idea, but with our Magellan package, we're trying to make it possible for people to easily develop and deploy different algorithms into a platform, right? It doesn't need to be all in one package, but something where you can easily develop something and just plug it in, right? So we're developing Magellan in that way, but CryoSparc is moving in that direction as well, opening up some parts of their software for making customized workflows. Relion also has some ways of doing that. So I think this is sort of the direction, is that we all recognize that deploying and supporting is sort of the hard part. And so, coming up with some community based initiatives to make it tractable, I think is going to be the challenge in the coming years.
Absolutely. Thank you.
This is actually a very validation kind of question. Unexpected features in the data, in this case images, but also metadata, are most often wrong. Sometimes they might be right and even very interesting. Could automated procedures like CryoSift have like an inherent risk of suppressing these unexpected but interesting features? And if so, how might you prevent it?
Yeah, thanks. That's a really interesting thought. So on the level of metadata being wrong, so CryoSift can, for example, if the pixel size is too wrong or like the CS value is wrong, you definitely see a degradation of your class quality. And if this is unexpected and it doesn't match other like live quality estimators, and just looking at the micrographs, you would have already a hint that there might be something wrong with your user input, and you might revisit your input as well and try to rerun it. The more interesting part on trying to figure out what is kind of on the sample level novel or beyond what you have expected, which is often the case. We have heterogeneity in the sample, oligomeric state that we didn't expect. So the user has control over selecting diameter range and extraction box sizes. And I always recommend, and also try to do this during my own data processing, to test outside of my expected particle diameters. And you can easily refeed it into the pipeline. So automation is really a key for this approach. So you can test your target, and then with a click of a button, you can just change your expected diameter and rerun the entire pipeline and compare the outputs. If there is, for example, a larger oligomer present or something new that you haven't expected yet to be part of your sample.
I have one final question. I promise it's the last one. What drove you to develop CryoSift?
There are many bottlenecks in this workflow, right? And many things where it's tedious, or you just don't have confidence in your the particular approach, right? And so in those cases, it's really useful to have a tool like this, where on the tedious side, it's just like I just want the answer. This is I need a tool that I have confidence in, that's going to select part in a standardized way and get me the result. So then you get through the tedium part, and then you can do something else that's more useful for your brain. But then on the other side, with a challenging particle, right, where you're going through and you're not sure what these data are telling you. Like, is this bad? Is the data bad? Is it junk? It's nice to have some metric to put on this class, so it's not just your eyes. And so where an advanced user like me might say, oh, there's something here. Maybe it's like some junk. Maybe we just need to keep poking on it. Whereas like a beginning user, they might think, this is all trash, throw it away, go back to the grid, go back to the microscope. So that's really, I think, what we were imagining when we were developing the tool.
Thank you very much. That was great. Right, so I think we've come to the end. I would like to thank the authors for joining us here today, and also the main editors and co-editor Stephen. Thank you for coming, and see you next time.
Thanks. This was fun.
Thanks. Bye.
Thank you. Bye-bye.
Bye.
Thank you.
Thank you.